This is unit number 3, video 13, Vsepr. In this section, we're going to look at geometries of molecules. Molecules have real geometries. We're drawing Lewis structures. Those structures give a two-dimensional look, and obviously the real world is three-dimensional. So most geometries actually don't fit well in the two-dimensional, so we can be deceived by looking at the Lewis structure and directly deducing geometry. You have to have some knowledge of the geometry. So there's going to be really three base geometries that we're going to look at. It's based on the number of electron clouds around the atom. I'm going to review those, a little chart we have, and then I'll show you some examples. Here we have the geometries that we're going to learn. These are the base octet organized geometries. Our primary 4-electron cloud geometry is tetrahedral. That's going to have 4 electron clouds and no lone pairs. There's two subs of that, trigonopyramidal and bent, where lone pairs start to show up. Then we're going to have trigonoplanar, only has 3 electron clouds, none of those are lone pairs. And then we're going to have a bent, in which there is a lone pair, and then we'll have a linear, where there's 2 and 0. You might say, well, what does that look like? Well, if we have tetrahedral, and let's just say we have some atom, X, a tetrahedral geometry is going to look like this. 4 bonds, no lone pairs. So we're calling these bonds clouds, because those electrons are not sitting on a straight line, right? There's 2 orbitals coming in, maybe s orbitals, overlapping, creating a bond. So it's a bulge of electrons, a cloud of electrons along this area. So here we have 4 of these clouds, none of those are lone pairs. That's a tetrahedral geometry. This bond angle is 109.5. Whereas if we draw it as a Lewis structure, it'll look like this. It looks like the bond angles are 90 degrees. They're not. They're 109.5 degrees, almost 20 degrees different, because it's spread out three-dimensionally. Now we go to trigonopyramidal. Now we're going to have a geometry that looks like that. So I have 3 bonds and 1 lone pair. 4 electron clouds. The lone pair is still a cloud. It's a little cloud sitting up there of electrons. Just no bond on the other side. No atom on the other side that created as a bond. So they're unshared electrons. Okay? The bond angle is still virtually 109.5. It'll actually be a little less than 109.5 because these electrons will try to get away from the lone pair. The lone pair tends to spread out because there's no protons on the other side to draw them into more of a line type shape. So that's going to be our trigonopyramidal 109.5. Now we go to bent. We're going to have X, lone pair, like that. Still 4 electron clouds. These 2 lone pairs are rotated like this. One's coming out of the board, the other's going back in the board. So there's still a 3-dimensional type geometry. This bond angle is less than 109.5, but pretty close to it. So we just say it's 109.5 or a little bit less. So that's going to be our bent. 4 electron clouds, 2 of those are lone pairs. Now we go back over here. So that was our 4 electron cloud sets. We could say, okay, what does trigonoplanar and bent look like here? Well, now we're going to have this type structure here. Okay? We have 120 degree angles. It sits in the flat plane of the board. So this is the one geometry in which it actually is sitting in the flat plane of the board. So we're dividing a circle into 3 parts. That's 120 degrees each, total of 360. And you can clearly see 3 electron clouds here. None of these are lone pairs. If we put a lone pair on there, now we're going to have the same type structure of the electron clouds, but one of them's a lone pair. We call this bent, because we're talking about the molecular geometry. So 3 electron clouds, because the lone pair is a cloud, but one of them is a lone pair. Bond angle is a little less than 120 degrees. Then our final one is linear. Linear, we're going to have this. Now we only have 2 electron clouds. So the electrons, which are repelling each other, I probably should have given a definition of Vsepr, is valence shell electron pair repulsion theory. The pairs of electrons are repelling each other. So these are repelling each other, boom, they go as far out as they possibly can. That's going to be 180 degrees. 180 degrees. Now, let me give you a couple examples, Lewis structures. CCl4, okay? I go through, I'm gonna have Cl, 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 Cl. 7 times 4 is 28, plus 4 is 32. So I have 32 valence electrons. 2, 4, 6, 8 have been drawn in bonds. So I have 24 electrons available to complete the octet. This carbon does not need any electrons. 2, 4, 6, 8, it's happy. Each chlorine has 2, needs 6. 6 times 4 is 24. So we need 24. Whenever our need equals our available, we just add the lone pairs. It's busy. Now we're going to analyze for the geometry. The geometry is going to come from the central atom. So this central atom has 1, 2, 3, 4 electron clouds. None of those are lone pairs. It's tetrahedral. That's a tetrahedral geometry. Matter of fact, we would draw that tetrahedrally like this. Okay, and that would be our tetrahedral structure for it. Okay, trigonal planar is going to look like this. If we have carbonate, we know carbonate is a negatively charged ion. We're going to have carbon in the center and 3 oxygens. Determine our valence electrons. We've got 4 for carbon. Each oxygen has 6. 6 times 3 is 18, plus 4 is 22. But we have 2 extra electrons. So we're going to add 2 into that 22 and make 24. So we have 24 valence electrons. I've already drawn 6. So 24 minus 6 is 18. So 18 available to complete the octets. Each oxygen needs 6 more to have an octet, because it already has 2. But carbon needs 2 more. 18 plus 2 is 20. So I need 20. Okay? If our need is not equal to our available, or the need is greater, we're going to add a bond. So I'm going to add 1 bond. 3 equally likely places, because each one of these oxygens would love to have 2 bonds. So what we're going to have is resonance. Okay? So I can draw all those resonance structures. I'm not going to do that here, but you know that the bond is equally likely in each place. Now, when we look at the geometry, that's really our focus, is the geometry. Even though this bond is equally likely, all bond lengths are the same, bond energies are all identical. Now, we've got 3 electron clouds on the carbon. We're going to treat the double bond as 1 electron cloud, because it is. Those electrons are together. So these electrons are trying to get away from this group of electrons here. Well, there's 3 electron clouds, no lone pairs. Notice, these external lone pairs, we're not counting towards lone pairs for geometry. Geometry is determined by the central atom. So, 3 electron clouds, no lone pairs. That is a trigonal planar geometry. You'd say, what does that look like? It looks like this. 1 oxygen here, 1 oxygen here, and 1 oxygen here, sitting in a flat plane.